So this is a video on GCSE Electrolysis. It deals with the electrolysis of molten substances only. So for electrolysis of things like aluminium oxide, which is the industrial case study of this topic, or the sulfuric acid, aqueous sulfuric acid electrolysis videos, they are done on separate videos. So this is pretty much an introduction to electrolysis, dealing, as I said, with molten ionic compounds, molten electrolytes, and also explaining the basis of an electrolysis and what it's all about. Let's look at the word electrolysis first and see what it actually means. So hopefully a lot of you will have picked up, I'm sure you'll have picked up on the fact that electro refers to the use of electricity in the process. Some of you may well have understood that the word lysis means to split. So essentially electrolysis means it's the conduction of electricity by an ionic compound. Okay, this ionic compound in this particular instance is called the electrolyte. That electrolyte has to be molten or dissolved in water, and that leads to the decomposition of the electrolyte. In other words, you're splitting an electrolyte, an ionic compound, up by using electricity. Now, why would we want to do that? Well, if you think of something like, let's say, for example, aluminium oxide, an ionic compound. If I can split aluminium oxide up, I can make aluminium, pure aluminium, and oxygen. Pure aluminium is widely used. You'll think of lots of uses of your aluminium, from making planes and trains and cars to step ladders, window frames, rulers, a whole load of uses, sinks. Okay, so you can make some very, very useful products from electrolysis. The problem with electrolysis is it costs a heck of a lot of money because it uses vast quantities of water and electricity primarily. So it says there, and we'll just deal with this slide a little bit longer. It says there that the ionic compound, which is called the electrolyte, in this instance has to be molten or dissolved in water. If you remember back to your first year of GCSE, you looked at the properties of ionic compounds, and you looked at when they could and they could not conduct electricity. And you found out that they could not conduct electricity as solids, but they can only conduct electricity as molten or when dissolved in water, because at that point the ions are free to move. But it's the ions that allow this electrolyte to actually conduct the electricity, and that's what leads to it being able to be turned into its elements. So very simply, what you do in electrolysis is you take a source of electricity, okay, whether it be a battery or a mains operated source, and you pass electricity through whatever that particular ionic electrolyte is. And the key thing is that you end up with the constituent elements. So no matter what you start off with in the electrolysis at GCSE, you end up with the constituent elements. So in electrolysis, the electrolyte is the liquid. Okay, that's your molten ionic compound, so make sure you're aware of the terminology. You know what the term electrolyte actually means, and of course you know that it has to be dissolved in water or molten for the ions to be free to move. We'll have a look at a quick video here on a quick video on what happens when ionic compounds dissolve in water, guys, just to clarify that concept for you.
Sodium
So that hopefully gives you an idea, guys, of what actually happens whenever substances dissolve in water. And the key thing that I suppose I want you to take from that is the fact that the ions at the end of that were free to move. And that's the whole point of it. The bonds within the ionic compound have been broken and the ions are now free to move. That's when it's dissolved in water. If you think about molten is very simply you heat it to such an extent that the ions break through the heat process rather than forming bonds with water. So let's look at this sort of fairly fundamental electrolysis setup that you'll have to know for GCSE. And you'll be asked to, I don't think you'll be asked to draw this, but you will probably be asked to label it. In fact, that has been a question many times. So you have electrodes, dipping into your electrolyte. You can see the electrodes here and here, and they're dipping into the electrolyte, which you can see here. Your electrodes are usually made from metal strips, but more often than not, they're going to be made from graphite in GCSE. The reason why we use particular metal strips or graphite is because, first of all, they're good conductors. That's primarily number one reason. Secondly, they are inert, so they don't react. Remember, they're going to be in hot ionic compounds here, so it's really important that they don't react. You might say, well, lots of metals are reactive, yeah, but we'll use things like platinum here, which are very, very inert, which are very unreactive. So if we do use a metal, it won't be a reactive one, okay? Well, certainly not at GCSE. That does actually happen on occasion. Okay, now when you're labeling this diagram, make sure, I'll point out the areas where people go wrong. So first of all, if you remember back to earlier in GCSE last year, you did ions and you did positive ions. And positive ions, if you can remember, were called cations, whereas negative ions are called anions. Now, you now have positive electrodes and negative electrodes, but the positive electrode is called the anode. So a lot of people get that mixed up because they think positive is associated with cat, and they think positive must be the cathode. I guess the way to remember it is that the positive electrode attracts anions, of course it does, okay? And I used to remember when I was your age as that anodes attract anions, cathodes attract cations. I could always remember that anions were negative, so therefore that reminded me that the cathode must have been positive. Likewise over here, cathodes attract cations, which are, as you hopefully can remember, positive. So cathodes attract cations. Cathodes themselves must be negative. Okay, I don't really mind how you remember it, just please try not to get the two things mixed up. The next thing, whenever you're labeling your electrolyte, label it molten electrolyte, whether it be lead, bromide, or whatever the examiner gives you. Okay, that's important. It has to be molten in order for the process to work. And finally, make sure you have some heat source, because obviously you've got to melt your lead bromide, okay? So, or whatever electrolyte the examiner gives you. Anything else? I know. Well, yeah, sometimes they put a bulb into it and they ask you what the bulb's for. Well, the bulb's just to prove that electricity is actually flowing and that the circuit is working. Okay. Well, let's look at a little bit more detail at the negative electrode. Okay, hopefully you can remember the negative electrode is called the cathode. Okay. And it attracts cations. So remember that cations are attracted to the cathode, and the positive electrode, which is of course the anode, okay, and the anode attracts anions. Right, we're going to look at a electrolysis here of lead bromide, and we're going to sort of develop this through into what might be a sort of considered an exam style question. So the first thing you might get is maybe to label apparatus. As I said earlier, I don't think you'll be asked to draw this. If you're asked students all around the country to draw this, you get all sorts of crazy diagrams and difficult to decipher pictures. Okay, so make sure you can label, okay, everything that's on there. I kind of pointed out everything from earlier on. This is a slightly different looking diagram, but it's pretty much the same. Right, now we've got to look at what actually happens at the cathode during this. So when I'm teaching this, what I would say is the first thing that you do when you're asked, and this is lead bromide, is you work out the formula of the compound. From that, then you work out the charges on the ions and the formula of the ions. So this has got lead ions in it, and it also has bromide ions. Okay, and that's really important because it's the ions that react at the cathode and the anode, so they will be what you are writing on the left-hand side of your arrow. Remember I said earlier in the slide that these always form their constituent elements, so the products are always going to be, in this case, lead and bromine, and that's really important for what's on the right-hand side of your arrow. So the lead 2+ ions are going to be attracted to the cathode, Okay, the cathode is of course the negative electrode, which we've already spoken about. This is the negative electrode here. So the lead, the Pb2 plus ions are going to be attracted to there. They're going to be turned into the constituent element I said earlier. That constituent element, as you can see in the red box, is lead. Remember, elements do not have a charge. So you will have things charged on the left-hand side, but you should never have anything charged on the right-hand side. If you have anything charged, apart from electrons, I should say, on the right-hand side, then you've gone wrong. So how many electrons do we need, and what side do we need them on? Well, we need 2 electrons. We need 2 electrons on the left-hand side because our lead is 2 plus. Our lead on the right-hand side, like everything, is 0 charge. Remember, charges have to balance. So if I have lead at 2 plus and I have 2 electrons, which is our negative 1 each, well, that equals 0. So that means that the left-hand side is now 0 and the right-hand side is now 0. The lead has gained the electrons. We show gaining of electrons by saying plus 2e minus, so that 2 electrons are being added to the lead. It's like adding, if I plus £100 into my bank account, I've added £100 to my bank account, and my bank account has gained £100, if you like. Okay, so it has gained electrons. Okay. And you need to know that when something gains electrons, you should know this from earlier this year in actual fact, that when something gains electrons, that is called reduction. So you will be asked to define the reaction as oxidation or reduction. So here the lead is plus the 2e minus, it's gaining the electrons, so it's being reduced. And you would have to state that. What would you say? Well, you're going to get lead, which is a metal. Okay, it's going to be hot, so it's going to be molten. And when a metal is molten, it forms silvery globules. Okay, so in this instance, there's various different words and phrases you can use to describe it, but silvery globules is a good one. That gives the impression of it being that sort of little beads of liquid, which is exactly what you would see. Okay, let's look at the anode, and the anode is going to attract the negative ion. The negative ion, as we'd already said up here, I'll just put it back up on the board. The negative ion is the bromide ions. Okay, and remember we said earlier that the bromide ion will turn into its constituent elements. The constituent element is bromine, so you need to be careful because remember bromine is diatomic, so you must write it as diatomic. Same would apply for hydrogen, chlorine, fluorine, iodine, nitrogen, oxygen. All those are all diatomic. So again, we have to balance out the charges. On the left-hand side, we have 2 bromide ions, which are minus 1 each, so you've got minus 2 in total on the left. The bromine, as I always said, has no charge. Any element has no charge. So we've got to make both sides the same, but we can only use electrons to do that. So if we bring 2 electrons onto this side, that gives us minus 2 on the right-hand side, minus 2 on the left-hand side. Charges are balanced. Now we show on the right hand side of this arrow, the plus sign tells me that the electrons in the bromine are now separate from each other, so the original bromide over here on the left hand side has lost its electrons. They're separate from it now. So loss of electrons is of course oxidation. Now what would we see in this instance? Well, we've got bromine being made, and bromine is a brown vapor. Okay, you might go, oh, no, it's not, sir. Bromine's a brown liquid. Well, it is a brown liquid at room temperature, but it boils at about 59 degrees Celsius. So in here, it's very, very hot, well over 59 degrees Celsius. So it becomes a brown vapor. And the other thing is, bromine, a bit like chlorine, smells of bleach. And you can get away with that observation for all of the halogens, that bleachy smell. Okay, the other thing about bromine, and you can get away with this for all the halogens as well, it's a good observation, is that all of these reactions when halogens are made have to be done in a fume cupboard because all the halogen gases are toxic. They're all poisonous. And sometimes they ask you that question, why must this reaction be done in a fume cupboard? And if there's a halogen being made, well, the reason is the halogen gas is poisonous. Don't just say it's poisonous. Be specific. Tell them exactly what gas it is. Okay. Right. So in these tasks, this is your task now, you're going to predict the products of both electrodes. You're going to write balanced half equations and label those reduction and oxidation. You're going to state the predicted observations at the cathode and the anode. Okay, and if there was a test for any gas that's made at the cathode or anode, you've got to say what that test would be. So I'm going to do lithium chloride as a worked example, and then you're going to do those 3. I will put the answers on the video. Okay, so you might want to, when I do the worked example here, you might want to pause the video and then do the other three. Okay, and then I'll put the other three, the answers, sorry, to the other three up on the screen. So let's have a look at lithium chloride here, first of all, on what we're sort of after. So there we go. I've done the formula of it to begin with, and I've worked out what ions are present in it. Again, that's very important. I've realized that at the cathode, my cations are made, and then that is turned into my element, which is just lithium. The total charge on the left-hand side with the lithium is +1, and on the right-hand side, as I always said, is 0. So therefore, I need 1 electron on the left-hand side to cancel out my +1. Okay, that means that my lithium here is gaining that electron. So therefore, that is a reduction reaction. And lithium, as if you look in the periodic table, is a metal, so it forms silver globules. If I go to the next one down, it was chloride ions, so I put my chloride ions on the left-hand side. That goes to chlorine. You always have to remember, like I said earlier, if it's diatomic, you have to write the formula of the element. Remember, it forms the constituent elements, so you never write just Cl. Chlorine as an element exists as Cl2. My total charge on the left-hand side I then have to remember to balance up my chloride ions. So I need 2 separate chloride ions. Never write the 2 on chloride ions down at the bottom right. That's completely incorrect. Chloride ions do not join together. They're both negatively charged, so they would actually repel each other. Okay, so I need 2 chloride ions on the left-hand side, and therefore I need 2 electrons on the right-hand side. Total charge on the left-hand side there is -2. Total charge on the right-hand side at the minute is 0. My 2 electrons bring that down to -2. Okay, that means that the electrons are lost. This positive sign here tells me that the electrons are separate from each other now. So electrons have been lost. That's oxidation. Okay, chlorine, you should know from your periodic table stuff last year, is greenish color, and it smells of bleach. So a pungent smelling or a bleachy smelling gas would be appropriate there. Your test for chlorine is that it turns damp blue litmus paper red, and then it turns it white. That's your standard test for chlorine. Might not be in all the GCSE specifications that, so you may or may not know that. Okay, so I'll go back to the questions. If you want to take maybe a photograph of those, I'll pause that for a few seconds, and then I will shift on to the answers. So I'll pause this for about 3 or 4 seconds here so you can write down 2, 3, 4 and 5, and then I'm going to move on to the answers. Okay, so there's the answers to the aluminium oxide. So there's your formula. Aluminium's 3+, oxides are 2-. Okay, so aluminium goes to pure aluminium, which is a metal, silver globules. Aluminium's 3+, needs 3 electrons to cancel out, so that's a reduction. 3 electrons have been gained. Okay, oxide ions are 2-, and they form diatomic pure oxygen. Okay, so I need to bring my 2 over to here to balance that out. Remember, there's 2 2-, so that's a 4- in total. So I need 4 electrons on the left-hand side to balance out those electrons. Observations here, well, oxygen is a colourless, odourless gas. You'll see bubbles of colourless, odourless gas, which relight a glowing splint. That is the standard test for oxygen. The positive sign here tells me that the electrons are no longer part of the oxygen, so the electrons have been lost. So that tells me that oxidation has occurred. Okay, hopefully you're getting the hang of this now. There's magnesium. You can see I've done the ions at the top. I've done the formulas there. Magnesium ion gains 2 electrons to become magnesium. It's gained 2 electrons, so it's reduction, and it's a metal, so silver globules is what the examiner will want. Nitrides, you just need to be a wee bit careful. They're in group 5, so they are 3 negative ions. They form, again, diatomic nitrogen gas. I need to balance out my 2s from my nitrogen with my 2 nitride ions, so I have a 2 here. That means that I have -6 in total on the left-hand side, and that means that I need to put 6 electrons in on the right. Nitrogen, as you know, is a colourless, odourless bubbles, colourless, odourless gas. I have shown that the electrons have been lost because they're now separate. That's what the plus sign tells me over here. So therefore 6 electrons have been lost, so that is oxidation. There's no test for nitrogen gas. The only test you do for nitrogen gas is you do all the other gas tests which come out negative. So you can assume therefore it's nitrogen gas. Let's move on to the next one. Oh, mustn't have done it. Okay, I'll go back and do it. Okay. So the last one was, oh no, it was magnesium nitrate. I've done it. Okay, so a calcium iodide. Where's calcium iodide? Calcium iodide has gone missing. All right, I'll just do it. I'll just do the calcium iodide here. Okay, so calcium iodide is CaI2. It has 1 calcium 2 plus ion, and it has 2 iodide ions in it. Okay, so if we do the anode, we'll do the anode first. So that attracts the anions. So that's I minus, and that goes to iodine. You should know is diatomic. I balance that out with a 2, and I need 2 electrons on this side, therefore. That is electrons being lost, hence the positive charge here, showing the iodine and the electrons are now separate from each other. So that is oxidation. Tricky little observations here, because iodine, it's very hot. Iodine is at room temperature a blacky grey solid, but because it's hot, it sublimes and it forms a purple vapour. So well done to anybody who was able to get that. Anything else I need? Test for iodine. Test for iodine is you can attach it or touch it with starch paper. Not sure many of you will have done that. And starch paper will turn a blue-black colour when iodine is present. Or you could bubble the iodine through starch, okay, and that would turn blue-black as well. Let's do the calcium at the cathode. So calcium ions are Ca2 plus. They go to pure calcium, which is Ca. 2 plus on the left and 0 on the right is the charges. So let's balance that out with 2 minus and 2 plus. Okay. The plus on the left tells me that the calcium is gaining those electrons, so that is reduction. Calcium is a metal, so that, again, nice and simple, silver or silvery globules would be your observation. And I think that's it. That's all the examiner would want from you, okay, on that particular one. Right, guys, I hope that helped. There's lots of past paper questions in your notes that you can have a go at. And you've got the booklet as well. So hopefully that clears up a lot on electrolysis for those of you who may be struggling a little bit. There are other videos on dilute sulfuric acid electrolysis, and there is a video on the case study for the electrolysis of aluminium oxide, which is bauxite, and the method to make industrial aluminium. Thank you.